3:14 a.m., a regional transmission network registers a local fault, and a single substation goes dark. The contingency alarms trigger. In exactly 47 seconds, the automated cascade-protection system will either isolate the fault or trip a sequence that drops 2.3 million people into the dark and inflicts over $800 million in immediate economic damage. The logic required to stop this specific structural collapse does not exist in standard electrical engineering manuals. To find the answer, the grid operator actually needs the principles of theoretical ecology and food web network resilience. This is a classic orphan problem. Two entirely separate scientific disciplines are staring at the exact same mathematical structure, preventing a localized node failure from causing a systemic cascade. But they lack a shared vocabulary to communicate about it. The electrical engineer describes system safety using the term N1 contingency. 3 buildings over, the theoretical ecologist describes the exact same mechanism as functional redundancy. The underlying architecture is identical. Human researchers rely on shared keywords to query databases. Because these two fields share absolutely zero surface text, standard literature research completely fails to connect them. This diagram maps standard agentic workflows. When typical data analysis fails to bridge a gap, we rely on the isolated node at the bottom, Agent 12, the general problem solver. Agent 12 operates as a domain-agnostic meta-reasoning loop, functioning independently of specialized training in grid physics or biology. Its core loop executes 3 steps. The system bypasses the retrieval of known data. It autonomously generates entirely new scientific claims through cross-disciplinary synthesis. Looking at the pipeline architecture, the operation begins with problem framing and the cross-domain scan. The system initially attempts to decompose the problem by slicing it into broad semantic categories, such as searching for general mechanisms. This approach is an immediate trap. Moving to the analogy search, the retrieval engine attempts to find matches using standard text embeddings. For this problem, surface text mapping is a guaranteed failure state. To find a match, the system abandons vocabulary for structural mapping. It aligns the underlying mathematics. It routes through the shared math layer using graph invariance. By measuring betweenness centrality, the engine links a biological keystone species directly to a critical transmission substation. Dropping lexical comparison in favor of mathematical relationships is the strict prerequisite for an AI to generate a valid cross-domain hypothesis. Once mapped, the agent moves into hypothesis synthesis and failure reflection. The first iteration produces a vague claim. The model outputs, resilience principles can inform grid strategies. This readout highlights a known failure mode called confidence inflation. The hypothesis is highly plausible and sounds intelligent, but it is completely untestable. To counter this, an independent evaluator requires a 0.70 combined score. The first attempt scores 0.40, 0.3 on specificity, 0.5 on grounding, and 0.4 on testability, because you cannot falsify a hand wave.
A tired human researcher looking at that text at 3 a.m. might actually accept it because it superficially looks like a defensible academic conclusion. The true engineering value of this pipeline isn't the text synthesis itself. It is forcing the agent to crash against an uncompromising logical rubric, so bad science never leaves the sandbox. Following rejection, the workflow moves to the final stage. The meta-learner logs the exact failure pattern and feeds it back into the initial ring step. The system generates a natural language refinement hint. It instructs the decomposer to completely abandon broad conceptual searches and focus exclusively on quantitative graph invariance. On the second pass, the agent breaks the problem down sharply, isolating betweenness centrality and network modularity. The revised hypothesis clears the gate with a combined score of 0.78. The final output explicitly states, power grids whose substation connectivity graph exhibits modularity and functional redundancy above ecological resilience thresholds will contain cascading failures to fewer than 5% of nodes. This achieves the delicate architectural balance of the system. It heavily penalizes vague abstractions while preventing the model from overfitting to prematurely concrete metrics that might be false for certain grid types. Because the loop logs every single iteration and refinement hint, human research teams inherit a fully auditable trail tracing exactly how the logic tightened. Structured, deliberate failure, and the subsequent meta-learning, is the actual engine driving autonomous scientific discovery. A zero-shot guess is simply not enough. Scaling out from this specific engineering problem, we're looking at a $15 billion shift in the AI research market by 2026. The landscape splits into two philosophies. At the base are massively integrated closed-loop frontier labs. These vertical systems brute force discoveries using immense foundation models trained on specialized biological data. Alternatively, the upper tiers feature open platform ecosystems from organizations like FutureHouse, Sakana AI, and Elicit. Because these platforms do not compete on raw compute scale, they rely heavily on the domain-agnostic multi-agent architecture of the general problem solver. The market validation for this auditable pipeline is clear in the numbers. Sakana AI reached a $2.6 billion valuation using these recursive improvement techniques, while platforms like FutureHouse secured massive philanthropic grants explicitly to build them. The divide is between the black box certainty of massive vertical models and the transparent logic of the open ecosystem, where scientists can verify exactly how an agent reasoned its way to a conclusion. The regional grid operator successfully averted the blackup because the agent's structural hypothesis provided a new operational baseline. By applying ecological modularity thresholds to the network's automated response, the system triggered a precise islanding of the fault that kept the failure contained to a single neighborhood. The grid held because a cross-disciplinary bridge was successfully built in real time, introducing a strategy that simply wasn't in the engineering manual that morning. Engineering priorities are shifting. The true competitive advantage in the AI space now lies in the creation of autonomous, multi-layered verification rubrics.